Hello, welcome to lesson 9. In this lesson, we are going to look at the sine conversion. We shall use the sine conversion also to look at calculation examples. And then lastly, we are going to look at the determination of the refractive index of a liquid using a convex lens of a known radii of curvature. Let us begin by looking at the sine conversion. The sine conversion is a rule for assigning either a positive or negative sign to the radii of curvature, or to the focal length, or to the image and object distances. In this case, we are going to look at the sine conversion for the radii of curvature. For a convex lens, the radii of curvature is positive, and for a concave lens, the radii of curvature is negative. Let us also look at the sine conversion for different types of lenses. We have what we call the biconvex lens, and this lens, both surfaces are convex, so it means that this is going to be having a positive radius of curvature, and this is also a positive radius of curvature. Then the plano-convex, this side is a flat surface, or it is a plane surface. The radii of curvature, so the radius of curvature is infinite, while for this convex side, the radius of curvature is positive. Then for the convex meniscus or the converging meniscus, the convex side is having a positive radius of curvature, and the concave side is having a negative radius of curvature. Then for a biconcave lens, both surfaces are concave, so this side is going to be having a negative radius of curvature, and even this side is also going to have a negative radius of curvature. Then for the plano-concave, the plane side has a radius of curvature which is infinite, and then the concave side has a negative radius of curvature. Then for the concave meniscus or the diverging meniscus, the concave side has a negative radius of curvature, and the convex surface has a positive radius of curvature. Now for the convex meniscus and then the concave meniscus, for you to know which one is going to take on the negative value, you look at the two values of the radius of curvature. The one which has a larger magnitude takes on the negative sign, and then one which has a smaller magnitude takes on the positive sign. Let's look at this example. A converging meniscus of radii of curvature 15 and 6 centimeters is made of glass of refractive index 1.5. Calculate its focal length when surrounded by Roman A, air, Roman 2, a liquid of refractive index 1.2. Now we are going to look at the first case where we are having air. And with the information here, according to this, you can now know that this is the larger value and this is the smaller value. So this will take on the negative sign, and this will take on the positive sign. So we shall have negative 15 and then positive 6 as the radii of curvature. So the convex side will have the positive, and then this will be the negative. So this R1 will be positive 6, R2 will be negative 15, and then the refractive index is 1.5, and it is surrounded by air. So we shall use the formula to get the focal length of this lens, that is 1 over f is equal to n minus 1 into brackets 1 over R1 plus 1 over R2. And when we use that, and we substitute for n with the 1.5, R1 with positive 6, and R2 with the negative 15, we shall have that. And therefore our f will be 20 centimeters. Then now when it is surrounded by a liquid of refractive index 1.2, so here we shall be moving from one media to another, so we shall use the general equation where we know that 1 over f is equal to n2 over n1 minus 1 into brackets 1 over R1 plus 1 over R2, where n1 in that case, or in this specific case, is going to be, the first media is going to be the liquid, so N2 is the liquid, and then the N1 is the liquid and N2 is the glass. So we are moving from liquid to glass because the media we are moving from, the surrounding media, is a liquid. So we are moving from a liquid, so that's N1, and then we're going to glass, which is N2. So it implies that we shall have our focal length given by 1 over F is equal to Ng over NL minus 1 into brackets 1 over R1 plus 1 over R2. Then after getting this, it implies that we are going to substitute for Ng, NL, R1, R2, and that will give us 1 over F is equal to Ng, which is 1.5 over NL, which is 1.2, minus 1 over 1 over 6 minus 1 over 15, because remember it is a plus, but the R2 is negative, so it gives you negative 1 over 15. And when we compute this, we shall get the focal length as 40 centimeters. So that will be the focal length of the lens when surrounded by a liquid of refractive index 1.2. Let us also look at this example here. A thin concave lens is placed in contact with a convex lens made of glass of refractive index 1.5, and its surfaces have radii of curvature 10 centimeters and 15 centimeters. If an object is placed 75 centimeters in front of the lens combination, gives an image on a screen at a distance 50 centimeters from the combination, capture the focal length of the concave lens. So they've given us the information about the convex lens, and they want us to get the focal length of the concave lens. So let us look at the information about the convex lens. We have 15 as one of the radius of curvature, and then 10 and then 15 as the other radius of curvature. And it is convex. It implies if you have just said it's convex, then it is biconvex in that case. So this is going to be positive, and this is also going to be positive radius of curvature. Then for refractive index of this is 1.5. Then when you look at the combination, we shall combine this convex and then with the concave, and we shall put our object at a distance of 75 centimeters, and the image will be at 50 centimeters. So the ray diagram will be looking like this. What we want is the focal length of the concave lens. Now we can use this information to get the focal length of the convex lens. Then we can use this ray diagram. Since we have the object distance and the image distance, we can also get the focal length of the combination. So let's get the focal length of the combination, and then we shall use the focal length of the combination to get the focal length of the concave lens, since we can also use this one to get the focal length of the convex lens. So first of all, we shall use this one. Using the lens formula, 1 over F is equal to 1 over U plus 1 over V, we can get the F, that is the focal length of the combination. And when we substitute, U is 75, V is 50, make F the subject, we shall have our F as 30 centimeters, which implies that the focal length of the lens combination is 30 centimeters. Then after that, we shall also get the focal length of the convex lens using the formula 1 over F is equal to 1 over F is equal to N minus 1 into brackets 1 over R1 plus 1 over R2. Now let us call the focal length of this convex lens F1. So we shall have 1 over F1 is equal to N1 minus 1 over R1 plus 1 over R2. Substitute for for N1, which is 1.5, R1, which is 10, R2 is 15. So when we substitute, we shall get our F1 as a 12 centimeters. So we shall have 12 centimeters as the focal length of this convex lens. Now we have the focal length of the convex lens, we have the focal length of the combination, so we can get the focal length of the concave lens using the combination formula 1 over F is equal to 1 over F1 plus 1 over F2, where F2 is the focal length of the concave lens. And shall make F2 the subject. From this equation, make F2 the subject, get the LCM here, which will be F1, F2, F1 as F2. But we need to make this on the subject, so it is better for you to first take this on this side. Shall have 1 over F2 is going to be 1 over F minus 1 over F1. Then after that we shall get the LCM as F1, F2, and then we shall have F1 minus F. And therefore, when we substitute in for F1 and F, we shall have our F2 as negative 20 centimeters. So you make F to the subject and you get it as negative 20 centimeters. So it is negative since it is a concave lens. Let's look at the determination of refractive index of a liquid using a convex lens of a known radii of curvature. So here, first of all, we shall get a lens of a known radii of curvature, and then we shall also have to get a plane mirror, which we shall place on a table with its reflecting surface facing upwards. Then we shall place the lens on that mirror. Then after that we shall clamp a pin horizontally such that its apex or its tip lies on the principal axis of the lens. And then we shall adjust, so it will be looking like this. Before, of course, this liquid will not be there before we place the liquid. We are first going to do the experiment without the liquid. That means that we shall be only considering the lens. We want to get the focal length of the lens first. So without the liquid, it will be like this. And then we shall move the pin. We shall move that pin. We shall move that pin upwards, up and down. We shall move it up and down until when its image, that is the image of the pin, coincides with the pin by the no parallax method. When we have achieved that, we shall measure the distance between the pin and the lens, and that distance is going to be recorded as F1. It's going to be recorded as F1. Then after that, we are going to remove the lens. We're going to remove the lens and then place in a little quantity of the specimen liquid on the plane mirror. So we shall remove the lens, place in a little quantity of liquid, and then we shall replace back the lens when you have placed the liquid. So when we replace the lens, we shall replace the lens and then repeat the procedure of getting the new position of coincidence. So we shall again move this, adjust the position of this pin until when the image of the pin coincides with the pin by the no parallax method. When that is achieved, we shall be having this setup like this, and therefore we shall measure the distance from the pin up to the lens, and that one will be recorded as F2. So we shall be having the focal length of the lens in the first circumstance, the first procedure, and then in the second procedure, that will give us the focal length of the lens combination. We shall be having the focal length of the lens combination. So since we shall be having now the two, we now need to get the focal length. So we need to get the focal length of the liquid lens. So because we have got the focal length of the lens, the convex lens, I've got the focal length of the lens combination, that is F2, and now we need the focal length of the liquid lens. So if we let FL be the focal length of the lens, the liquid lens, of that liquid lens, then we are going to get the focal length of the liquid lens using the formula 1 over F2 is equal to 1 over F plus 1 over FL. And then using that, we shall also get the refractive index of the liquid. So this is what we are going to be having. We shall get the focal length of the liquid lens using this equation, and then we shall use this equation after getting the FL from this equation. We shall substitute in this other equation, that is the full thin lens equation, to calculate the refractive index of the liquid using this formula. This is what we shall. Of course, here what we are going to do is that we are going to make NL the subject, because we are looking for the refractive index of the liquid. We shall make it the subject, and when we make it the subject, we shall be having NL is equal to 1 minus r over fl. Now, how did we come up with this? We need to note that when we are looking at this lens combination, the upper lens is a convex lens. Now the lower lens, that is the liquid lens, is going to be a plano concave. Remember, the refractive the radii of curvature of the convex lens is known. Let's say it is r. So if it is r, it means that the upper surface of the liquid lens is going to have a negative radii of curvature because it is concave. For the liquid lens, it's going to be concave, so it's going to be negative r. It's going to take on negative r because it is concave. And then the lower surface of the liquid lens is going to take on an infinite radius of curvature. Now when we substitute, it means that r1 is going to be negative r, and then r2 is going to be infinity. So 1 over r1 is going to be 1 over negative r, and then 1 over infinity is going to be 0. So we shall have 1 over r plus 0, which will be 1 over r. And that's how we get this equation here. That's how we get the equation, where r is the radius of curvature, is the radii of curvature of the convex lens. Yeah. Thank you for your attention. We meet in the next lesson.